So in this lecture we will look at the clock distribution network, the basics, the terminologies, the topologies, etc. The clock signals are special signals. They have some characteristics which are different from what the normal signals, and so we have to take special care while routing them. As you can see here, this is the clock tree distributed from the source to probably hundreds of sinks. So the clock signals are loaded with the highest fan out because they have to distribute the clock to hundreds of flip-flops. They travel over the longest distance. As you can see here, it starts from here and then gets distributed in this fashion, and so they traverse the entire length and breadth of the chip, and they operate with the highest speed because they are carrying the clock signal. So they typically toggle every time period, every single time period, and hence they dissipate quite an amount of power. Now this is the representation of a typical clock distribution network. We have the clock from the source here. The clock is generated on chip using a PLL, phase lock loop, as a frequency multiplier from a crystal, and then it gets distributed in this fashion. And the wire which distributes the clock has got resistance and capacitance, and so we show it like this symbolically. And then here we have the flip-flops to which the clock is distributed. Now the buffers are inserted in a typical clock distribution network. Now why should we have buffers? Any clock distribution network relies on buffer stages to amplify the clock signal from the source, the clock generated, to the clock sinks, because the clock signals travel through the clock tree, and the wires have got resistance and capacitance, so they tend to get degraded. And another reason is that to reduce propagation delay or the clock latency. You know that from your basics of digital IC design that the signal propagation delay increases quadratically with wire length. So it is only advantageous if I split this wire of this much length into 3 segments by having buffers. And the third important reason is that the buffers are used to avoid the capacitance being accumulated. See, for example, here, now this buffer has to drive the wire capacitance of this much length and the input capacitance of these 3 flip-flops. Now, so if we don't have this and this buffer, right, and this buffer too, if I don't have any of the buffers, then the clock here has to drive not only the input capacitance of these many flip-flops, but also the wire capacitance of wires of this much length. But then having buffers avoids the capacitance being accumulated. That is what we have said here. The distributed buffers serve the double function of amplifying the clock signal degraded by the interconnect impedance, and also isolating the local clock nets from upstream load impedance. Right? So in other words, I would say that this buffer is designed to drive the wire at its output, the wire capacitance plus the input capacitance of these 3 buffers. That is enough. Okay. Now we'll introduce some basic terminologies. Some of them are very basic. We start with what is called as the clock latency. See, clock latency is basically the propagation delay of the clock through the clock distribution network. And so we say that if there is a clock here and it gets distributed from here to 2 flip-flops, then we say that the clock's at source, and then we observe the clock at flip-flop 1, and we say that this is the clock latency, or in other words the propagation delay of the clock through the clock network. Now we will also have what is called as clock skew. Clock skew is a spatial variation in the arrival time of the clock signal at the clock sinks. So I have the source here, and this is just a simple example, but I have just discussed now that a typical clock distribution network is buffered, and in deep submicron technology we know that buffers are they have process variations, manufacturing variations, and because of which we will have unwanted delay. So even though you might design this clock network such that the clock reaches flip-flop 1 and flip-flop 2 at the same time, if you are going to, in a typical clock distribution network which is buffered, the clock may not reach both the flip-flops at the same time, and which we are going to call it as clock skew between flip-flop 1 and flip-flop 2. As I already said that the major sources of this clock skew are on-die process variations, the loading variations, and other unintentional design mismatches. But however, clock skew is a static uncertainty, which means when I switch on this circuit and I start distributing the clock, if the clock is reaching flip-flop 2, say 10 picoseconds delayed when compared to the time at which it reaches flip-flop 1, we say that the clock skew is 10 picoseconds, and it remains 10 picoseconds for the entire duration for which this chip is on. It doesn't vary with time. It's a static uncertainty. There is also another uncertainty which is dynamic, and that we call it clock jitter. Clock jitter is a temporal variation in the arrival time of the clock signal at sinks, and the major sources of such a variation being dynamic voltage variations. Again, I said that if you have, because the clock distribution network is buffered, buffers are fed by VDD, and if there is a change in the VDD, it's going to affect the propagation delay, which in turn is going to affect the skew. There is also temperature gradient in the chip due to activity variations. A part of the chip may be at a higher temperature, and you know that temperature affects electron mobility, which in turn affects the transistor speed. Now there can also be a jitter in the clock generator itself, and that also translates as clock jitter. But jitter is a dynamic uncertainty. So if you have the clock at flip-flop 2, if I measure 2 cycles, I have cycle 1 having time period T1, and I have cycle 2 having time period T2. Now T1 may not be equal to T2, though it's ideally supposed to be the same. If I'm distributing a 1 GHz clock, T1 is supposed to be 1 nanosecond, and T2 is also supposed to be 1 nanosecond. So, but they may not be the same, and that we call it clock jitter. The clock slew is a measure of the reconstruction capability of the buffers, how faithful the buffers are in reconstructing the clock signal. You see, the buffer is nothing but a cascaded inverter like this, and so if I have to drive, if this buffer is supposed to drive a load, you know, whatever is the flip-flops it has to drive, the input capacitance of the flip-flop and the wire capacitance, I'm lumping it as C load. And so if I have a 1 GHz clock and the clock has a rise time of 100 picoseconds, then here also the clock must be having a rise time of 100 picoseconds. Now if the buffer is not designed well, it may not be able to drive it, or it may not, this signal may not rise at the time at the rate of 100 picoseconds, right? So what I'm saying here is that supposing if the buffer is not designed well, then the clock may slew. It may take time to rise like this. That is something which we don't want. That we call it clock slew. So typically the rise time or the fall time must be, 10%, lesser than 10% of time period. So that's why he said for 1 nanosecond time period, 1 GHz clock time period is 1 nanosecond. The rise time can be 100 picosecond, 10% of that. We don't want it to be beyond that. It should not deviate from the accepted norm. Now, broadly speaking, the clock distribution network can be classified as either a clock tree or a clock mesh. Now, in tree, there is a single path from the source to the sinks. You have the clock from the source being distributed. So for all the sinks here, at least for all this group of sinks, there is a single path from the source to the sinks. While in a clock mesh, if you see here, for the sinks here and sinks here, the clock can reach through any of these buffers, right? So a mesh is nothing but a horizontal wire segments shorted, connected like this horizontally and vertically, so that the clock is available in all these segments. So wherever you have the sink, you can just connect them. And typically mesh is used in distribution where the density of the clock sink is high, especially in microprocessors where you have a dense distribution of clock sinks. So it may not be very efficient to have a tree, because as I said here, in a tree we must try to have a unique path from the source up to at least a group of sinks. And when you have a large distribution of sinks in a small area, it is better to have a mesh. The mesh are also, the clock mesh are also really resistant to process variations, to the skew induced by process variations, as we'll see. Now the clock tree, there are some sub-topologies in a clock tree. Now here we have what is called as an unconstrained tree. An unconstrained tree is a clock network that is designed with a cost function that minimizes the delay differences across all branches. Now an unconstrained tree doesn't have any structural matching, as you can see. Wherever I need a clock, I just take from the main. If I say this is the main branch and these are the sub branch, and again I can just take a sub branch here, and I must make sure that the delays in all these branches are balanced so that the clock reaches all the sinks at the same time. Doesn't have a structural matching. The H tree, as shown here, is an example of a balanced tree. So a balanced tree is a tree with a structural symmetry and exhibits identical delay, buffer and interconnect segments from the root, that is from here to the sinks. So you can see that from here to the sinks, the length of the wire is the same and even the number of buffers is the same. So a balanced tree has got zero structural skew. Okay, you be careful that I am saying that this is zero structural skew. It's not zero skew exactly, because when you have so many buffers, there can be variations, skew induced by process variations, but which will be minimum. But assuming that all the buffers are perfect, I will not have any skew. The clock will reach all these 4 plus 4 plus 4 plus 4, 16 points at the same time. Now the tree which we initially displayed is also called a binary tree. Now a binary tree is intended to deliver the clock in a balanced manner in either horizontal or in a vertical direction. So here I can say that it is distributing the clock in a vertical dimension. Now this is different from a balanced tree, which is designed to span the entire area in both horizontal and vertical dimensions. Remember this balanced tree, you have the top H here, and then each from here you have other H, right? So it's growing horizontally, and each stage maybe you can have this H and a lower metal layer than this, so you can keep going towards the active region in the chip. So it grows horizontally and vertically. A binary tree may also have crosslinks. These are some of the improvements to the basic binary tree, where if you feel that the clock latency through this path and this path are too much out of balance, you might have a cross link, we may just short them by a wire, and so the cross links are inserted at specific points to equalize the clock latency. Now a typical microprocessor today might have a combination of all these topologies. So this is one of the clock distribution methodology in a microprocessor. So you have the reference clock and we have the phase clock loop acting as a frequency multiplier, and so here we have the clock which has to be distributed, and you can see that we are having a H tree here, and then we have other local trees. You can have a local mesh, and these are some of the common structures. We call this the trunk and then the tree, a H tree here, and remember this is also a mesh because you can see at this layer the output of all the three buffers are shorted, and at this layer the output of all these buffers are shorted. So basically then you have, if you have a group of clock sinks connected here, you have multiple paths for the clock to reach the sinks from the source here. So this is also a mesh. This is the actual clock distribution in a Pentium 4 processor from a IEEE paper. So you have from the PLL here we have a middle spine, we have a top spine, we have a bottom spine, and the clock gets distributed. So we may have a combination of topologies to distribute the clock. Now, having introduced you to topologies, now we must understand how a clock distribution network is analyzed. We have to calculate or analyze the skew. We have to calculate the power dissipated. So the clock tree or a clock mesh is modeled using some wire models. Now you know that these are some of the famous models for the wire. These are famous distributed RC models, and we have the pi model here, the T model, and the L model. Generally pi model is known to be very accurate, and so we may model the wire using the pi model for the wire. So here I have shown a clock mesh of 2 rows and 2 columns here, and this can be modeled like this. Okay, now here I have shown a clock tree. I'm feeding a clock to this node U, and then it gets split into 2 nodes, and from node V again it gets split into 2 nodes Y and Z. Now assume that all these wire segments are pi modeled. So here I'm replacing this segment of the wire by its pi model. That means resistance Ry. Okay, I call it by the resistance of the node to which is connected. So this is Rz, this is Rv, and then there's an Ru, and this is Rx. Okay, and then I've got 2 capacitance, C by 2 and C by 2, where C is the capacitance of this wire segment. Okay, so again here I have a wire segment, so I have C by 2 here and C by 2 here. Again here I have a wire segment, so I have C by 2 here and C by 2 here. So, and those capacitances are added, are lumped here. So this can be an equivalent RC tree of this clock topology, clock network topology. So a tree topology here on the left, and its equivalent network is shown here. And now I am interested in calculating the clock latency. Now there are 2 ways. One is we can go for a SPICE simulation. There are SPICE tools like the ngSpice, which is an open source tools. We may use the tool to connect series of RC segments like this and feed a clock at the source and find the clock latency. There is also another model called the Elmore Delay model, which is a very famous model, which can be used to find the clock latency. Now, an Elmore delay is used to calculate the delay from the source node to a particular node in an RC tree. Okay, and this is how it is defined, that the Elmore delay from the source to a node I is the summation over n nodes in the tree, and I'm going to start from k being from the first node till the nth node, the capacitance at the node into what is called as the effective resistance. The effective resistance is the resistance between the input node and the node k in common to the node from the input node to the node at which you want to find the delay. Right? I'll give an example. This is the Elmore delay to a node I, to a particular node I, is the summation of the RC product terms, where you start from the node, first node till the nth node, the capacitance at that node into the effective resistance, where the effective resistance is the resistance in common from the source to the node k in common to the source to the node I. We will see an example that will illustrate this better. Now, how do you find the Elmore delay in this clock network? Remember, the Elmore delay is also always defined from the source to a particular node in a clock tree. Okay. Now, here I am going to find the Elmore delay to the node V. Now, remember, there are 5 nodes, I believe. 1, 2, 3, 4, 5. 5 nodes with capacitance. So we start with this node Cu into, remember, I am interested in finding the Elmore delay to the node V. Resistance in common from the source to the node U in common to the source to the node for which you want to find the Elmore delay. So it is Cu into Ru, right? And Cv into Ru plus Rv. Cx, let me illustrate. Cs is the node here. Cx into resistance in the path from the source to the node x in common to from the source to the node you want to find the Elmore delay. So what is the common resistance? The common resistance is only R. Right. Similarly, Cy into resistance from the source to the node Y. We have from the source to the node Y in common with from the source to the node you want to find the Elmore delay, that is till V. So the common resistance is Ru plus Rv, right? And finally Cz into, Cz is here, resistance from the source to the node Z in common with the resistance from the source to the node V. So the common resistance is again Ru plus R. I hope it's clear. So this is the Elmore delay to the node V, and that is going to be, if we take Ru common and Rv, we can find the Elmore delay is Ru into Cu plus Cv plus Cx plus Cy plus Cz plus Rv into Cv plus Cy plus Cz. Now, Elmore delay to the node Z, by using a similar exercise you can find that the Elmore delay to the node Z is this. Okay, so we observe that an interesting relationship between Elmore delay to the node V and Elmore delay to the node Z. The Elmore delay to the node Z is the Elmore delay to the node V plus the resistance leading to that node into the total sub-tree capacitance. Remember, I repeat, the Elmore delay to the node Z is the Elmore delay to its parent node from the source to the parent node, that is Elmore delay to the node V, plus the resistance leading to that node into the total subtree capacitance at that node Z. In this case, we have only capacitance Cz, so it just becomes Rz into Cz. Now, just to make what I said more clearer, we have the Elmore delay to the node V. In this equation, we have the Elmore delay to the node V, and here I have the Elmore delay to the node U. So as I said, the Elmore delay to the node V is the Elmore delay to its parent node, as the Elmore delay to the node U, plus the resistance leading to that node, into the total subtree capacitance. The resistance leading to that node into the total subtree capacitance. So this is the subtree at node V, has capacitance CV plus CY plus CZ. So we have the Elmore delay to the node V is the Elmore delay to the node U plus the resistance leading to that node RV into CV plus CY plus CZ. So in other words, the Elmore delay of a node is an accumulation of the RC product terms from the voltage source to the node of interest. And this is what I just illustrated, that the RC product term at the node K is that of the branch resistance RK and the total downstream capacitance CTK. So what we are essentially saying is that in a top-down manner, from the voltage source to the node I, we can sum up the RC delay, and in fact in a top-down traversal of the tree, we can compute the Elmore delay for all the nodes. Now these are the two references. The Clocking in Modern VLSI Systems by Xanthopoulos is an excellent book dedicated only to clock distribution systems and all the complexities and the issues in modern clock distribution networks. And you can also go through this book, especially for the Elmore delay modeling. I have taken the material from this book, Synthesis of Clock and Ground, Power and Ground Networks, from this chapter 13 of this book, Electronic Design Automation. Thank you.